All right, pre-calculators, pre-calculus people, pre-calculators. That sounds good. Let's go through this. What we're doing today is complex zeros and the fundamental theorem of algebra. Why are we doing it? Well, we got to figure out the two theorems, figure out complex conjugate zeros, and factoring with real number coefficients, because we need to understand how real number coefficients work. Okay, so the fundamental theorem of algebra. If a polynomial function of n degree, the third degree, let's say, it'll have three complex roots. 1, 2, 3 complex roots. This one is a real root, and then you have two imaginary roots. Now, imaginary roots will always come in conjugate pairs if you have real coefficients. Okay? All right, so this is a basic function. Here are the roots. We'll get to how to figure those roots out in a little bit. But the fundamental theorem of algebra, if it's like x to the 8th power, it's going to have 8 roots. If it's x to the 5th power, it's going to have 5 roots, and so on. Okay, that's what this is basically saying. All right, here we go. So, the fundamental polynomial complex conjugates, and so on. If negative 3i is a root, then 3i is a root. So this root would be 3i, this one would be negative 3i, because you set them equal to 0 and solve. Okay? So if we multiply them together, we get x squared plus 9. And you go, what? How did they get that? Well, they don't really explain it here very well. So this is what I do. I use the formula x squared plus the sum of the roots I think it should be minus sum of the roots times x plus the product of the roots. We'll see where the plus and minus sign is here in a second. So if you take the roots, 3i and negative 3i, and you add them up, 3i plus negative 3i is 0. That's their sum. Now if you take 3i times negative 3i, and you get negative 9i squared, which I squared we all know is negative 1, times a negative 9 is a positive 9. So the product of the roots is 9. So it's x squared minus 0x plus 9, or x squared plus 9. X squared plus 9 would factor into x plus 3i, x minus 3i. Okay? Now, there are no zeros of the function because there's no x-intercept. So we really can't call these zeros of the function. They're roots of the function, but not zeros. All right. So let's take this example. What are the roots of this? Okay. Well, the roots are 3, 3 minus I. So its conjugate pair is 3 plus I. Come on, Mr. Bierschbach, get it together. 3 plus I. And then this one is 2 plus 5i. So then you'll have a 2 minus 5i. So using the fundamental theorem of algebra, it's going to be x to the 5th power is going to be the highest degree of it because we have 5 roots here. So x plus 3 is a root from this one. X minus 3 minus I is from that one. X minus 3 plus I is from that one. And then x minus 2 plus 5i and x minus 2 minus 5i. Okay, that's really ugly looking. We could multiply that all out, but we don't want to. We want to use some of the roots product of the roots. Okay, so x plus 3 is that one. This one, its sum is 6. If we add these together, it's 6. The product we get is when we FOIL it, 3 plus I times 3 minus I. 3 times 3 is 9. Outers and inners and conjugate pairs always cancel. Minus I squared. So 9 minus I squared is 9 minus a negative 1, or 9 plus 1, which is 10. So this product is 10. So it's x squared minus 3 minus 6x. Come on. Minus 6x plus 10. Okay, this one, their sum is 4. Add them up because these cancel. Sum is 4. Their product is 2 plus 5i times 2 minus 5i is 4. Outers and inners cancel. Minus 25i squared, or 4 plus 25, which is 29. So the product is 29. So it's x squared minus 4x plus 29. Now, yeah, it's the hard part. We have to FOIL or multiply these together. Not really FOIL, it's triple distribute. So x plus 3, x squared times x squared is x to the 4th. X squared times negative 4x is negative 4x to the 3rd, plus 29x squared. Then you take negative 6x times each of them. So it's negative 6x cubed plus 24x squared minus 144x. I'm pretty sure that's right. Then plus 10x squared minus 40x plus 290. Okay. So it's x plus 3 times x to the 4th, negative 4x to the 3rd minus 6x to the 3rd is minus 10x to the 3rd. 29x squared plus 24x squared is 53x squared, so it's plus 63x squared. And then x, it's a negative 144 minus 40, which is negative 184x plus 290. And then you have to double distribute the x plus 3 through. So it's x to the 5th minus 10x to the 4th plus 63x cubed minus 184x squared plus 290x. I multiply the x times each of those. And now I multiply the 3 times all of them. Plus 3x to the 4th minus 30x cubed plus 189x squared minus something x. 3 times 4 is 12. Carry the 1. 3 times 8 is 24. With the 1 is 25. Carry the 2. 3 times 1 is 3 plus 2 is 5. So 552x plus 290 gives me a 0, a 7. Carry the 2. So we got 870. So now if we combine like terms, it's x to the 5th minus 7x to the 4th plus 33x cubed plus 5x squared. 552 and 290 is minus 262x plus 870. Okay, I did this all without a calculator. Hopefully I'm right. And they did the math, and Oh, 352 instead of 262 and 25. Yeah, I made a couple of mistakes in there. But yeah, done all the way out. They did it the long way. I did it a little different way. But we both got to there. And then it's just, yeah, trying to multiply this bad boy out to there. We won't do much of this today. Okay? But you will have a little bit of that. Not to the fifth power, hopefully, though. All right. So if we have real coefficients, how do we factor it? Well, that's what we've been doing, the rational root theorem. The factors of 9 over the factors of 3 are 1, 3, 9. 9 over 3 is 3. 9 over 1 is 9. 3 over 3 is 1. 3 over 1 is 3. 1 over 3. And that's plus or minus for all of these. So it has 4 possible real rational roots. They did synthetic division. They found negative 1/3 was one of them. And then they factored out and kept factoring. And that's what they got. Okay? Factoring a polynomial. And we'll practice that a little bit more tomorrow than today. So if it has an odd degree, it'll have at least one real zero because conjugates always come in pairs. So if it's an odd degree, it'll always have one real zero, and then the other ones come in conjugate pairs. That's something you have to worry about too much. Okay, now discard. Now what we're going to do is go here. I don't want 2.6a. That's what we'll do on Friday. 2.5a. We're going to look at some of these quick. Okay, so it says, write the polynomial function in standard form. Standard form would be when we multiply it through. So if we FOIL that, it's x squared. Outers and inners are going to cancel. Minus 9i squared, which is x squared plus 9. So it's x squared plus 9. Because I squared is negative 1, multiply. There we go. The zeros of the function are 3i and negative 3i. And my pen is way too fat. Let's go with this one. Okay. X-intercepts. There are no x-intercepts because the only roots are imaginary. When your only roots are imaginary, there's no real roots. Okay. This one. If we FOIL this, okay, this x minus 6 times x minus 6 is x squared minus 12x plus 36. This one, if we FOIL, we get x squared minus 49i squared, so it's plus 49. And then we just FOIL or multiply. So it's x to the fourth plus 49x squared. Okay, we got x squared we multiplied through. Then negative 12 times x squared is negative 12x cubed. And then 12 times 49. Time to grab the calculator. 12 times 49 equals 588. So minus 588x. Done with that one. And then take 36 times each of those. So then it's plus 36x squared, and then 36 times 49 is 1764. So these are the only two like terms. So it'd be x to the fourth minus 12x cubed plus 85x squared minus 588x plus 1764. The zeros of the function are 6, and it's a double root. We'll talk about double roots in a second. Negative 7i and 7i. But you don't need to list double root. It's just, there we go. X-intercepts are at 6. Okay, because that's a real root that crosses the axis there. Okay. If it's 6i and negative 6i, it's x minus 6i times x plus 6i. So it's x squared plus 36 is the way it works out. All right. Polynomial function like this. We've done enough of this right now. We have x minus 1 times x plus 2i times x minus 2i. You can FOIL this, so it's x minus 1 times x squared plus 4, and you FOIL it and put them in. Same thing with this. Okay, multiplicity, or how many roots it has. Okay, if it has a multiplicity of 2, it's x minus 1 squared. If it has a multiplicity of 3, it's x plus 4 cubed. Okay, so write a polynomial function of minimum degree with a standard form with real coefficients and zeros and blah, 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 blah. Okay, so we multiply this out. X minus 1 times x minus 1 times x plus 4 times x plus 4 times x plus 4. So x minus 1 times x minus 1 is x squared minus 2x plus 1. X minus 4 times x minus 4 is x squared plus 8x plus 16 times x plus 4. So if we multiply those through, we get x cubed plus 8x squared plus 16x plus 4x squared plus 32x plus 64. Take x times each of them, take 4 times each of them. So x squared minus 2x plus 1 times x cubed plus 12x squared plus 48x plus 64. And then you multiply those two together. And then in the end, you'll get this. Okay, so multiplicity of 2, x minus 2 times x minus 2. Okay, you always use the opposite sign. 3 plus I has a multiplicity of 1, so it's x plus 3 plus I. All right, x minus 3 plus I. And they always come in conjugate pairs. So then it's x minus 3 minus I. And here's where I do the sum and product of the roots. So it's 3 plus I and 3 minus I. So their sum is 6. Their product is 9 plus 1. Their product is 10. Okay, because if you do outers and inners, they cancel. 3 times 3 is 9. I times I is negative I squared, which is plus 1. So that's how we get 10. So it's x squared minus 4x minus plus 4 times x squared minus 6x plus 10. X squared minus the sum of the roots times x plus the product of the roots. You FOIL, double, distribute, whatever. You put the answer there. All right. So looking at graphs and multiplicity, if something has a multiplicity of 3, it's going to flatten out but cross the x-axis. If it has a multiplicity of 2, it's going to bounce on the x-axis. If it has a multiplicity of 4, it's going to bounce on the x-axis, but it's going to bounce wider than a multiplicity of 2. Okay, so you can match things up. So this would have a multiplicity of 2, this would have a multiplicity of 3. So we want to have negative 3 with a multiplicity of 2, and 4 with a multiplicity of 3. Here, this has a multiplicity of 3, this one has a multiplicity of 2. So 4 has a multiplicity of 2, and negative 3 has a multiplicity of 3, and so on. So that's how you figure out what graphs go where. How many complex roots does this function have? And how many reals does it have? Well, if it's to the second power, it'll either have 2 complex or 0 complex. So to figure this out, we can try to factor it. and ain't no factoring is going to happen there. You could complete the square, which I think is the easiest. X squared minus 2x plus blank plus 26 minus blank. Okay? So then half of this squared, half of this is -1, 1 squared is 1. So it's really x minus 1 quantity squared plus 25. So that equals 0. Move it over. X minus 1 equals negative 25. Take the square root of each side, because this is squared. When you take the square root, x minus 1 equals negative 5i here, plus or minus 5i actually, because the square root of negative 25 is 5i, and you got to be in conjugate pairs. So x equals 1 plus or minus 5i. So these are two complex roots, so they're two complex, 0 reals in this situation. Okay, completing the square. Just set this equal to 0 and solve. Okay. All right, that's going to be your assignment.